Welcome to the Math Record. Today we'll be covering the rules for derivatives. This video will cover part 2 of chapter 2 in our calculus class. Let's start with understanding the rules for limits first and then use those to understand derivatives. Okay, so let's say we have two equations. We have f of x, and let's say that's 2x minus 1. And we have g of x, and we'll say that's 3x plus 4. So generally, for a bunch of these rules, they follow the basic arithmetic sequences, so they're not really that complicated. If you understand your basic arithmetic rules, then it's basically the same. So let's say we have a constant, right? So usually the general idea is the limit as x approaches 2. The equation is just 3. There's no variables or anything, just the number 3. Then basically it's just got to stay that number. So it's just going to be 3. So this is the constant, which is generally the same. So if we try something like, let's say, limit of x approaches 2 of 3 times f of x, right? We could say this is the same thing as saying 3 times the limit as x approaches 2 of f of x. This is true, right? So let's just say 2, we plug it into this equation. So we have 3 times f of x, which is 3 times 2 of x, which is 6 of x. And negative 1 times 3 is negative 3. So we have limit of x approaches 2 of 6x minus 3. So plug in 2 here, so that's 12. 12 minus 3 is 9. So that's 9. And now let's try this portion. So limit of x approaches 2 of f of x. So plug in 2 in here. So 2 times 2 is 4. 4 minus 1 is 3. So there's a 3 here. Times the 3 that you just got is 9. So just because you multiply a number, which we call is referred to as a scalar. Just because we multiply this by a scalar doesn't mean that it's gonna change the ending result. Because we move it from the limit in or outside that limit, because it's generally gonna be the same thing. So when I say it does follow the arithmetic rules, they really do. It's really, really basic for adding, subtracting, multiplying, and dividing, or even with radicals and powers. They're generally all the same. So let's go back. So let's say we have 2x minus 1, and we have 3x plus 4, right? So now let's try adding them. So we have limit as x approaches 2. It could be any number. I'm just choosing 2 as an example. You could choose any number for x. And we'll have f of x plus g of x. You can write this as the same as limit of x approaches 2 of f of x plus limit of x approaches 2 of g of x. Which is true, right? So we have 2x plus 3x, which is 5x. Negative 1 plus 4 is plus 3. And let's plug in 2. So 5 times 2 is 10. 10 plus 3 is 13. And now we could do this individually. So f of x approaches 2, so that's 4, and that's 3. And approaches 2, that's 6, and that's 10. 3 plus 10 is 13. This is the same thing. Because if you split up into parts, they should generally be the same. Because for orders of operation, right, you do the arithmetic first, and then you do the limit. So even if you do the arithmetic later, which you're just substituting for x, the final value doesn't really change. So all these rules generally just follow the arithmetic. So it's not really that much of learning, but if you understand the concept, we could use this to find the derivatives, which is pretty neat to understand how they function in the end. So subtraction, generally the same idea. So 2x minus 1, 3x plus 4. So we have limit of x approaches 2 of f of x minus g of x. So same thing, limit of x approaches 2 of f of x minus limit of x approaches 2 of g of x. Right? The same case as the plus, but now instead it's a minus. So 2 minus 3x is negative x. Negative 1 minus 4 is negative 5. So plug in 2, so negative 2 minus 5 is negative 7. You can also prove it here, because this is the same. So 2 here, that's 4, that's 3. That's 6, and that's 10. So 3 minus 10, -7. Right? They're the same thing. Just because we split them up into parts doesn't mean they're going to be different in the end. Same thing with multiplying. So we have, just so you don't forget, 2x minus 1 and 3x plus 4. Limit as x approaches 2. And we have f of x times g of x. Right? You could just say this is limit as x approaches 2 of f of x times the limit of x approaches 2 of g of x. You can't change these numbers if you're splitting up into parts, like for adding and subtracting. You can't, or multiplying and dividing. You cannot change this. Like if you say this is initially 2, you can't suddenly change this to a 1 and a 3. These has to be the same numbers. It has to be the same limits. Okay? So if you're multiplying them together, that would be 6x squared. That's 8. That's -3. So that's plus 5x. This is minus 4. So plugging that in, that's 4. That's 24. That's 10. And that's minus 4. So altogether, that's 30. Right? Now, if we do it individually, that's 4. And that's 3. That's 6. And that's 10. So 3 times 10 is 30. Right? It's the same thing. So instead of doing all this work, we could just do it individually by parts, and then we could just multiply them into n, which is generally the same concept. And you could also do this for division, right? So we have 2x minus 1 and 3x plus 4. So limit of x approaches 2 of f of x divided by g of x is the same thing as limit as x approaches 2 of f of x divided by the limit as x approaches, sorry, I'm kind of running out of room, x approaches 2 of g of x, okay? Sorry, that's a little bad. G of x, okay? So if you do this by here, so that's 2x minus 1, 3x plus 4. So that's 4, that's plug in 2, so that's 3, and this is 6, sorry, this is 10, so that's 3/10. Or you could do this by parts. So limit of x approaches 2 of f of x, that's 4, that's 3, all over g of x. Limit of x approaches 2 of g of x, so that's 6, and that's 10. And we just do that individually by parts. So it keeps track of all these the same. So if we use this with the power rule, right, let's try a different equation. So let's say we have limit as x approaches 2 of, let's say, like equation x of a, you know? So a is some kind of number. So this would be the same idea as limit as x approaches 2 of x and raise to the power of a. So it's the same concept, right? So let's say a is equal to like 5, like 3, actually. Let's say 3. So we have x cubed. So let's erase this a little first. So I'll show you the example. So x approaches 3. So the limit of x approaches 3, that's 8, right? So 2 times 2 times 2, because this is power 3, if I kind of wrote as constant. X to the power 3, that's 8, right? So we could just try limit of x approaches 2 of x, and then raise that to a power of 3. So that's 2. Limit of x approaches 2 of x. So as x approaches 2, it's just got to be 2. So it's just 2 to the power of 3 is 8. And that's basically the power rule for this. These might not be the general term, the power rule, subtraction rule, but it's generally how I remember them. So, or you could also do these with radicals. So you have like a limit as x approaches 2. And let's say we have like the square root of like 2x minus 1, right? So we could plug that in, that's 4 and that's 3, so this ends up at square root 3, right? Or you could just have limit of x approaches 2 of 2x minus 1, and then you square root that entire thing. So that's 4, and then 4 minus 1 is 3, and this, don't forget the square root from the beginnings, and that's just square root 3. It's the same idea. So for basic like arithmetics, the concepts just follow the same rules, and those are the general ideas for limits. So let's use these concepts and now let's apply them to our derivatives and see how they work. So for constants, let's say we have an equation f of x, right? Our 2x minus 1, and our g of x, which is our 3x plus 4, right? So we're not always going to be using f of x and g of x all the time, but I'm using them to show examples. So our constant rule, right? So if we have, instead of using limits, how we denote derivatives is that we kind of use these apostrophes. So we have f, and then we write an apostrophe, and then x. F apostrophe x, which is what we call the derivative of x, of f, is what we call the derivative of f. If you want to be more specific of the function, like you just call it derivative of f of x, like it doesn't really matter. It's the general point is that they know it's a derivative if you put an apostrophe there. So that's one way to write it. Another way they usually write it is they call it d of d of dx of f of x. So it basically just gets the general idea of what this means is that it gives the derivative of f of x in respect to d of x. So this d kind of just means like a really, really small change. And that gets back to the idea of calculus, which we just use small amounts of change to come together to make these really big changes. So this d would just mean small amounts of change. It might seem like a lot of like complicated math, but all these breakdowns to are just really, really small notations. So we have this. So each notation is fine. I usually rely on the apostrophe because it's more clean, but these is also valid. It doesn't matter which way you use. Sometimes some people are more picky over the other, so it doesn't so you might want to prefer one over the other, but usually I just use the first method because it's just simpler. And it's easier to remember because sometimes you might have variables like d and x, and you don't know if you have to like cancel them out, so it's harder to keep track of. But apostrophe is good. So what we have is 2 times the derivative of f of x, and this is basically saying we have the derivative at that point, which is the constant. So if we have derivative of this, if we use the general idea of what we have in chapter 2, part 1 in our previous video, we have x and f of x, right? And we have x plus h all over f of x plus h, right? So we plug that in here, we have x and 2x minus 1, and we have x plus h. So plug x plus h into x, that gets 2x plus 2h minus 1. So to find the derivative is basically just 2x plus 2h minus 1 minus the 2x minus 1 here. So this 2x cancel out this 2x, this negative 1 cancel out this negative 1, so you only have the 2x, right? This is just changing y over the change in x. So you only have 2h on the bottom. And then you have x plus h minus the x. So this x cancels out this x, and you're just left with h. So 2h divided by h is 2. So as the limit, as h approaches 0, right? Because there's always a limit to find the instantaneous rate of change. Because the first part that you always do, the slope is what is the average. So as h approaches 0, that ending amount, which is 2, that will give us the instantaneous slope, which is 2, because there's no h left over. So as I said before, using the limit rule for constant. So this is going to be our slope, basic instantaneous slope. So if we had to use this idea, okay, let me delete this. Okay. So we have 2 times derivative of f. We have 2 times our derivative was 2, which makes 4. So this is the general idea of how the constant one works. You can also do the same thing with derivatives for adding and subtracting. Oops, sorry about that. Okay. So if we have the f derivative of x plus the derivative of g, right? Our derivative of x, f is 2. Our derivative of g of x, we could do that again. So we have x and f of x. And we have x plus h of f of x plus h, right? This is the general idea that always works for derivatives. You could always do it, but later on in the video, I'll teach you a faster method, which you don't have to always do this work to find the derivative, because it seems like a lot of work to do something so simple. So for now, we're going to use this general idea, and we're going to help derive it. So we have g of x, derivative of g in respect the derivative of g of x, which is 3x plus 4, and this x coordinate, and we have x plus h. So substitute x plus h into x, we have 3x. So 3 times x is 3x, 3 times h is 3h, and then we have that 4 left over, plus the 4, right? So 3x plus 3h plus 4 minus the 3x plus 4. So this 3x cancel out this 3x, this 4 cancel out this 4, so you're only left with 3h. All over, so it should change in y, so now we need to change in x, which is x plus h minus the x. So the x cancels out, and we only get the h. So the 3h divided by h is just 3. So that gives us the average. So now we just need to find the instantaneous, which is just limit as x approaches 0, because we want x to be really, really small. Because as h approaches 0, not x, h approaches 0. So as h approaches 0, it becomes really, really small. So h becomes a really small number. That's why it's approaching 0. So as it approaches like a really small number, then this value and this value becomes super small. So they becomes, the h becomes super small. So then like x, this value and this value becomes like really, really close together. Because let's say this is like 2 and h is like 0.1. So this will like 2.1, which seems a little bit far. So let's say h is 0.01, right? And then 0.001, 0.0001, right? It gets closer, closer, and closer, and you could get like at 1 point. And that's what we do for instantaneous rate of change with limits, if I didn't explain it earlier clearly enough. So for derivative, that's 3, because as limit as h approaches 0 of 3, it's the same idea when I did for f of x, it's just 3. So we just have the limit of g of x is 3, I'll write it right here. So 2 plus 3 is 5. So the derivatives just follow the same rule. So as like limits, so it basically follows the same basic algebras. So as I shown before with the constant and the adding. And now we could also just do the subtraction. So we have f of x and 2x minus 1 and g of x, and that's 3x plus 4. Okay, we're not going to do the derivatives again because I just showed in the like a few minutes ago that the derivative of f is 2 and the derivative of g is 3. So we're just going to use this idea. So we have the derivative of x minus the derivative of g is equal to just 2 minus 3, which is negative 1. Which, don't forget to know which side it is, because g of f, the derivative of g minus the derivative of x, is not the same thing as saying the derivative of x minus the derivative of g. So you have to follow those basic arithmetic ideas. So now it will be like 3 minus 2, because derivative of g of x is 3, and derivative of f of x is 2, so 3 minus 2 is 1. So this top part is negative 1, and this is 1. So self-explanatory of how this works. So, but those are only for adding and subtracting. Subtracting. For derivatives, for the multiply and divides, there is several rules that you need to know, which is a little which are a little strange. Just because if you're multiplying like these equations together, they become new equations that you might that had different properties than actually limits. So let's try something like we have f of x, right? We have 2x minus 1. And we have g of x, and that was 3x plus 4, right? So now we have derivative of x is equal to 2. We said that before. I said it a few minutes ago. G of x is 3. This is just the same example. I'm just rewriting it again. Now, for the multiplying rule, the derivative, if we have f of x, right, times g of x, and we want to find the derivative of this, right? We want the derivative. This is apostrophe. Sorry if it didn't look clear. Let's write right here, apostrophe. So the derivative of f of x times g of x, this is written as the derivative of x times g of x plus plus f of x times the derivative of x. So this is the general formula that you have to follow all the time, every single time that you're finding a derivative of a product of two equations. So how do you remember this? This is actually really simple. So you see where the derivative gone? It just goes on both sides of the equation. So generally, you just do the derivative of one equation and then multiply by the equation of the other one, by the normal equation of the other one, not the derivative. And then you add it to the derivative of the other one, multiplied by the regular derivative of the original one. So you have the derivative of the x multiplied by the regular of the g plus the regular of the f times the derivative of the g. So that's just the general idea of how to multiply it. So how would this work? So if we want to find like derivative of x is 2, derivative of g of x, g of x, not the derivative, is 3x plus 4. So this is 3x plus 4 plus f of x, the regular equation, not the derivative, so 2x minus 1, times the derivative of g, which is 3. So multiplying that out, that's 6x plus 8, right on top here. And this right here is 6x minus 3, right? So if you add these together, 6x plus 8 and 6x plus 3, that makes 12x plus, sorry, I'll write this a little closer in your room, 12x plus 5, right? So this is the general idea for multiplying for limits, which is true. So the reason it kind of works differently is that for this case, I'll explain why. We have two linears, and if we multiply two linears together, we get a quadratic. And there's a rule that I didn't introduce yet, which talks about how these limits work for polynomials, which is with a quadratic is a polynomial. And that's why it works differently, because if you do it this way, if you just do it with limits, you're missing some parts out of the derivative. That the change in derivative if in relation to f of x times g of x. So every single time you have f of x times g of x as you're multiplying them together as a derivative, you have to follow this rule all the time. But it's still pretty basic. So if you just follow this rule like numerous times, more and more, it kind of gets ingrained into how you do derivatives. You just memorize it as you go on, because it's like one of the fundamental rules that you just need to understand. So that was for multiplying. And now let's try dividing. So we have f of x of 2x minus 1. And the derivative of that was 2, right? Using this example again. And we have 3x plus 4. And we have derivative of x is 3. So we're going to divide this, which is going to be derivative. So, sorry, f of x times f of x divided by g of x. And then we're going to take the derivative of this, of f of x divided by g of x. The idea of this one is basically this almost the same idea for the product, except now you're gonna divide by something. So we're gonna have the product rule kind of on the top. So the derivative of f of x times the regular of g of x, right? Plus the regular of x times the derivative of g of x, right? And then we're gonna divide this by uh, g, uh sorry by g of x squared. So I won't say why you have to divide by g of x squared, but how to differentiate, how to memorize these equations, the product and the quotient for derivatives, is that if you just remember that on the bottom for dividing, you have to divide by some kind of equation. So then for the derivative, you need to divide by the square of that equation. So if we had to do the derivative of f of x divided by g of f of x divided by g of x and derivative of that, then basically we just need to do this. So we have 2 derivative of x, 2, times the regular of g. So that's 2 times 3x plus 4. So that's 6x plus 8. And we have f of x times the regular of f of x times the derivative of g of x, which is 3. So 3 times 2x minus 1 is plus 6x minus 3, right? This is what we got for the product rule in our previous example. So that's 12x minus 5, right? I mean 12x plus 5. And now you have to, now this time you have to divide by g of x squared. So now you have 3x plus 4, and now you square it. So this is going to be your derivative, which is going to simplify to 12x plus 5 divided by 3x plus 4. See? That's why derivatives are a little bit more complicated when you're multiplying and dividing, because it sometimes leaves these equations like these, which seem a lot more complicated than the original equations of f of x and g of x. And somehow you just get these equations. So that's the dividing rule. As I said before, with the multiplying, the more you use it, the more you memorize it. So just remember, it's derivative of the f. Sorry, oops. I misspoke. This is not a plus, this is a minus. Sorry about that. This is a minus. So 6 of x plus 8 minus 6 of x minus 3. So 6x minus 6x is 0. 8 minus negative 3 is plus 11. This is 11. Sorry about that. So the derivative of this for products is basically a derivative of one of them times the original of the other, plus the derivative of the other times the original of the original, times the derivative of the original one, right? So it's basically this idea on top, but instead of the minus, it's a plus. Now for the dividing, you have the same idea. The derivative of the top one first, always. You can't do the g of x, derivative of g of x times f of x first. It has to be the derivative of the top one, the numerator, times the regular equation of the denominator, right, the g of x, minus the original equation of the numerator, times the derivative of the denominator, divided all by the square of the denominator equation, the regular equation, not the derivative. So this is the example. So you could just connect it back and forth. Sorry about like having it plus in the beginning. It's actually 11. You have to minus it. So dividing, how do I remember which one uses which? When you're multiplying, you're mostly trying to increase something. Multiply, I rationally think it's usually something that's bigger, so you use plus. Dividing is usually something you get smaller, so I use minus. And that's how I remember which sign to use. And then you just have to memorize the general idea of the derivatives, where they are, and the g of x squared if you're dividing. Okay? And that's for the dividing rule. Now, we're going to do something a lot more basic, which is the constant rule. Which is basically, let's say you have an equation like f of x, and that is 2. If you take the derivative of f of x of 2, it's going to be 0. Anything that was constant, like 3, 4, 5, let's say even like irregular number like pi, like, you know, like you use that for circles. Yeah, it's gotta be 0. If you take the derivative of a number, it's gotta be 0. And you can't split them up like limits. So you can't say, like, let's say you have f of x of 2 of x. You can't just say the derivative of the 2, which is 0, and then take the derivative of the 2 is 0, and then take the derivative of the x to get like 1 or something, and then you have 0 times 1 is 0, so the derivative of f of x is equal to 0. That is not true. You cannot do that. So the derivative of this is actually going to be 2. So you can't just say it's 0 just because the constant, if you take a derivative of a constant, 0. These are two different things. These are not equivalent. But that's the constant rule. If you do a derivative of a constant, then you're going to get of a constant number like 2, 3, 4, 5, -2, any number, just a constant, will be 0. So even for the case of 0, so if you take the derivative, let's say f of x is 0, and we take the derivative of 0, it's going to be 0. So it works for all constant terms all the time. So, and now we're going to learn something that is the power rule. This is the one that I referred to earlier in the video, which is how you memorize, how I know to do these derivatives without doing a lot of work. So basically, the general idea is like, let's say we have f of x, right? And we have derivative x to the power of a, right? A is some kind of number, like let's say it's polynomial x squared or something, you know? So the general idea is that you take the derivative of f is equal to, you move the, whatever you have in the exponent, move it down as a constant. So it's going to be a times x, whatever you have in the exponent, you minus 1 from it. All the time, x minus 1. So this is your derivative, a times x to x minus 1. So how does that work? So let's just say we have something like f of x is equal to, like, let's say 5x squared, right? So if we take the derivative of that, we already have 5. So that's a constant. This is made up of two things. It's constant and a power. So we could just leave the 5 there and then multiply. Because the derivative of this, we just move 5 away, right? So then we just say derivative of x. Then we just have to find the derivative of x squared, basically, right? So the constant will affect it, just like it just doesn't affect, because that's the constant rule for derivatives. So you have 5. So the derivative of x squared, move the 2 on the bottom, right? And then times x is always x. And then 2 minus 1 is 1. So this will get up to 10x. So I used in a video of this equation for 5x squared. And in our previous video, and got a derivative of 10x using the idea of limits with x and f of x and x plus h and f of x plus h. And we did all the math out to find the average slope and then use limits to find the instantaneous slope to get this number. Well, this is the power rule, and this is the general idea of how you're going to do this. So it doesn't matter even if it's like not a quadratic or a linear. Like if this is a linear, right? So we have 5x, right? F of x is equal to 5x. Take the derivative of that is 5, right? Because x is the power of 1. So move 1 to the bottom, so it's just 5 times 1. And x, 1 minus 1 is 0. So anything to a power of 0 in exponents, right? Normal math is basically, it's just 1. So it's just 5 times 1 times 1. So it's just 5. And that's how I know that the derivative of 2 is 2. Because it's just going to be the coefficient that's left over. And that's the power rule. So this is the rule that you want to know. Like, fundamentally know. This is the one of the sorry about that. One of the fundamental rules of calculus. So if you just understand this rule, it's basically the same. But this only works for polynomials because those are the only things raised to powers. You cannot apply this rule to to exponents. Even though it seems like you cannot. Because exponents work by a different property. Instead of having the number in the exponents, like x squared, we're going to have 2 to the power of x, which is different because x is on the top now. So we had to use a different rule for that, which we'll cover in a future video. So that's the idea of the power rule. And now there's something else in derivatives which we introduce now, which is called the chain rule. This rule is really important because let's try like an equation like f of g of like f g and a of x, you know, right? So we have 3 equations, right? We have f. If you ignore all this, like if we take all this out, we just call that x, right? We have f of x, right? So we have 3 equations in here. We have f of x, we have g of x, and we have a of x. And we have a of x is inside g of x, and g of x is inside f of x. So technically, we have a of x inside g of x, which is inside f of x. So we have 3 equations together in one. But we're not adding them, we're not multiplying them, we're not dividing them, or we're not subtracting them, and we're not like using constants or like power rules. So what are we doing? We're chaining them basically. So how do we find the derivative of this? So the apostrophe, sorry if it kind of looks bad. So, and that's why sometimes we want to use d of x, right? So d of x of f of g of a of x, right? So we want to find this, which is easier to understand than using apostrophes. And that's why I taught both ways, just in case if you wanted to use it that way. Okay? So the general idea for chain rule is that you do the derivatives inside out. I mean outside in. So basically is you do the derivative of the front one and then you keep anything that's inside the same and then you do the derivative of that one. So what we do is basically we have f of x outside, right? So we do the derivative of f and then you're gonna leave the g and a of x inside. Right? And that's how you're gonna chain it. So where does the chain part come from? Well, the chain part comes from having this number, I mean this equation, and you gotta multiply it by basically derivatives of other numbers. So this is your first chain, and then you gotta multiply this by the equation inside. So now you already did the outside, which is f of x. Now you're just gonna worry about this now. So now you're gonna do the derivative of g. So the derivative of g, you're going to multiply. Any single time you chain, you're going to multiply those numbers. So derivative of g of x times the inside, which is a of x. That's the only thing you have left inside. Right? But you already still have something inside. So you're going to keep working until you do everything. So then you're going to multiply by the derivative of a of x. And that's all. Because if you chain like x, which is the last thing inside, it's just the derivative of x, which is the derivative of x, which basically just be 1. So it's basically the same thing. Because you're taking the derivative in relation to x. Every single time you're doing calculus, if you're using x as your x-axis, right? You have x-axis and your y-axis. If you're taking it in relation to your x-axis, then you're going to do it with respect to x. So if you do the derivative of just x by itself, it's just going to be 1. So if you're doing something like a time versus like versus height, you know, then basically you're gonna do it with respect to time because that's your x. So if your time is like using variable t, then derivative of t is 1. It's generally the same idea with x and t. You're just using a different variable. So it doesn't really matter. And that's your general idea for chain rule. So let's kind of apply this. Let's show an example. So let's say we have 2x. Let's actually label this. We have f of x is equal to 2x cubed, right? And then minus x minus 5. And let's say we have g of x is equal to 2x squared plus 3 or something, no? And let's say we have a of x is equal to 4x minus 7. right? So every single time we work with this, let's say we want to chain this, right? We have f of g of x and a of x inside of that g of x. Let's actually use different colors so we could represent this better, right? So let's use blue, and we'll say that is f of x. So we have f of, sorry if that's kind of hard to see. So we have f of x outside, right? And now we're going to use red for g. So we have g of x. And now we're going to use yellow. And we'll have that as a of x. Right? So this is how we're going to chain them. So go back to white again. We're always going to use this for a derivative. So we take the derivative of this function. And how we're going to do this. So basically, first thing we're going to do is we're going to work outside in. So we're going to do the derivative of f of x. So instead of like plugging all these in and then find the derivative using the power rule, because, you know, if you plug it in, you could just expand it out as a larger polynomial. That's tedious and it takes too much work. So what we're going to do is that we're going to use the chain rule. So the chain rule is basically, we're going to do the derivative of outside and then we're going to go in. So what we're going to do is that we're going to first take the derivative of f, because f is the equation outside, right? Because you have f of x, and then the g of x, and then the a of x. So take that derivative of f of x using the power rule, right? Would just be the coefficient times x to the power 3. So move the 3 down, so times 3. And then the x. x3, right, minus 1. So the exponent minus 1 is 2. Right? So using the power rule, you get 3x squared from x cubed. The more you do with it, you kind of see the trend. So whatever you have, like x3, the first derivative, 3x squared. You can have multiple derivatives, so you can take the derivative of 3x squared, which just be 2 times 3 is 6. So the more you do it, you kind of just like derivative of 6x is 6. So you kind of just see the patterns, and you don't have to put too much effort into like know when you have to subtract. So it just becomes kind of second nature. So the derivative of negative x, negative 1 in front, so derivative of x is just negative 1, right? And the derivative of a constant is 5. So you can always split up to derivatives in parts. So you could take the derivative of this one, then the derivative of this one, then the derivative of this one, right? So we could just have, so the derivative of f of x, in this case is 2 times 3 is 6, is 6x squared minus 1, right? From here. So that's our derivative, 6x squared minus 1. And that's what we have. So we have derivative of x, which is 6x squared minus 1. So I'm going to leave the x squared blank. And because we need the g times ax squared. So we're going to have to leave that inside. So we have g of ax, and then the g, right? And I'm switching between colors. So we have the original of the derivative of f of x squared minus 1, right? Because it was 6x squared minus 1. But whenever you do the derivative, you're going to leave whatever you have still inside the parentheses still inside. So you left so inside the parentheses was the g of a of x, so you have to leave the g of a of x inside. So this is our equation, right? And then we're going to multiply this by the derivative of the inside. So you already worked with the g of x, I mean the f of x, so now you have to work with the g of x. After the g of x, you're going to work with a of x. So it just seems a lot of tedious work, but it's faster than actually doing something by combining, expanding these out. Imagine putting g of x inside of x here on the cubic. So you have 2x squared plus 3, and then you have to cube that, and then you expand that out. You have to expand that out, you have to multiply the 2, and then you combine them together. Or, like, it's more work, you have the a of x, you have to put the 4x minus 7 into the g of x, and put that g of x into f of x, which is a lot of work, which is a lot faster if you want to do for derivatives. So, now we just need to do the derivative of g of x. So, the derivative of g of x is just 2 times that 2, which is 4. And then you have the x. So it's just because you move the 2 down, and then 2 minus 1 is 1, right? So the 2 times that 2 is just 4. So it just becomes second nature, and it gets really fast. And that's why, even though it might seem like we're taking so much time using the chain rule right now, I'm just slowing it down so you understand. But it's super, super fast once you understand how it works. You'll be doing derivatives left and right super fast. It's really easy. So for this, for g of x, the 3 is just constant, so it's just going to be 0. Derivative of a constant is just 0. So this is just 4 of x, right? So as always, you're going to, every single time you see an x, you're going to leave that as what you have still inside the parentheses. So you did the g of x, so what is still inside the parentheses? Only the yellow part, which is a of x. So the derivative was f of x, so that x is substituted with a of x. So we have times a of x. And now we just need to take the derivative of a of x. So the derivative of a of x is just 4x minus 7. Derivative of 4 is just 4x is just 4. Derivative of negative 7 is just 0. So the derivative of ax is just 4. So derivative here. And that's how you work inside out, right? So you have f, so this is a chain rule. So review, basically, derivative of f is 2x minus 3 minus x minus 5. Derivative of this is 6x squared minus 1. And that's why you have the 6, and then whatever's left in the parentheses, you put that in as your x, and then you square that minus 1. And then whatever's left in your parentheses, you have to do the derivative of that. So you have to do the derivative of g of x. So the derivative of g of x is 4x. So for the x, you always substitute whatever's still left inside. In this case, we have a of x, so you plug that in. Now the derivative of a of x is 4. So you just have 4. So this is the equation for the derivative of f of g of x of a of x. Now let's try something that incorporates a lot of these rules. So let's say we have using the same equations. Let's say we have f of x is the 2x cubed minus x minus 5, right? And we have our g of x, which is equal to 2x squared plus 3. And we have our a of x, which is 4x, which is equal to 4x minus 7. So let's say we have an equation like f of x times g of a of x, right? So we have multiple things going on. We have the product rule. We have the product rule because we have f of x, one equation, the f of x, multiplying the g of a of x. And we have the chain rule going on because we have the a of x inside the g of x. So we have multiple steps we need to do. So basically, we have the first thing we always do is that we do whatever's outside, and then we're gonna work with whatever is left. So basically, since we see the product rule first, we're gonna do the product rule basically first, right? It will be different if we have g of f of x inside times a of x. So what we do is that we do the chain rule first, because chain rule is inside, because there's functions inside. So we do the derivative of g first, and then we're going to do the derivative of this. And then the derivative of this would be a product rule, because we have to do, because we have two products right here. So for this example, it's different. So these are not the same. These are not the same. So we have f of x times the g of a of x. So that's the first thing we need to do. We need to first understand what we need to do. This was that might have seemed long to understand what we need to do, but as you do more and more, it becomes really obvious of what you have to do first. So how you know what to do? Well, basically you just follow the same rules. So the first thing you see is the product rule, so we need to do the product rule. So it's going to be derivative of x times the regular equation, which is g of a of x, right? So that's usually what I do. I usually like to write everything out. And then plus the normal equation of x, right? Times the derivative of g. But when you do the derivative of this, right? The derivative of this, you have to chain it. So now we just have to do the chain rule. So put a big parentheses because we had to chain it. derivative of g, and then leave what's inside, which is a of x. And then you have to multiply, because every single time you do a chain rule, you always multiply. You don't add anything. So whatever you chain, you multiply, multiply, multiply. You keep multiplying. So whatever's inside, you do a chain of it. So derivative of a of x is just a of x. Derivative of a of x. Right? So that's all we have to do. So now we have to find the derivative of... Sorry, I don't know why this is here. Just ignore this a little bit. Actually, we could just delete. So, something right here. Okay. Let's go back again. So, separate this. So, the derivative of f of x is, we need to find the derivative of x, which is just 3 times 2 is 6. And then you subtract 1 from that 3 is 2. And the derivative of x right here is negative 1. Right? So, and then you multiply by g of g of x, which is just 2x plus 3. But now you have the x is now substituted with a of x, so you have to substitute this. So you have times 2 of a x squared, which is 4x minus 7. Right? And then squared. And then plus 3. And now we have a really big equation. And that's why, even though this might seem really simple, or somewhat simple right now, if you do the derivative, it takes a lot of work. So, we have this. And now we have to add. Okay, so I'm kind of running out of room. So, let's move this up. Kind of just remember the equation. And we have this still left over. Okay. So the derivative, the regular equation of f of x, that was 2x cubed minus x minus 5. And then multiply by the chain rule of g. So the derivative of g was right here, so that's 4x. But the x is substituted by a of x, remember, because we chained it, which is basically 4x by 7. And then you have to multiply this, which would be our g prime of x, would be just this. The g prime, or you could just say prime, it doesn't matter. Prime and derivatives is the same thing. So g of prime of a of x times the derivative of a of x, which is just, derivative of a of x is just 4. Because x, which is 1 on top, 4 times 1 is 4, and then 1 minus that 1 minus 1, 1 from the exponent minus 1 is 0. So this just be 0. And derivative of a constant just is 0. So this is your derivative equation. 6x squared minus 1 times 2 times 4x minus 7, that's raised to a power 2, and then plus 3. And all in parentheses multiplied by 6x squared minus 1. Plus, those things multiplied plus the 2x cubed minus x minus 5, that's in the parentheses, multiplied by the parentheses, 4 times x minus 4 times another 4. So we gotta have to put another parentheses in here that I forgot. So you have to add, you multiply these together, and you have to add them together, and that's your derivative. But basically, when you do calculus, you don't really have to simplify all this to make like a perfect polynomial. Usually when they ask a derivative, they're going to ask a derivative at a point. So let's say they want the derivative of f times g of x of a of x at x equals 1, right? Now you just have to plug 1 into the equation. So that would be like 6. 1 squared is 6. 6 minus 1 is 5. And then you have 4, that's negative 3. Negative 3 squared is 9. 9 times 2 is 18. 18 plus 3 is 21. So it's 5 times 21 plus. Right, you plug in 1 here, so that's 1. So 2 times 1 minus 1, that's just 1. So 1 minus 5 is negative 4. Plus negative 4. Times 4 times the 4x minus 7. So plug in 1 here, that's 4. 4 minus 7 is negative 3. And then you still have a 4 here. So this is 105. -4 times -4 times 4 is -16 times 3 is 48 times another 4, which is 96, and 192, I believe. Which we could just, if you do the math in the calculator, I'm not exactly sure. It could be 192. I just assume it is, and you could add them together is 297, right? So the derivative of x is equal 1 is 297, which is the slope at that point. So it seems like a really large number because it really is if you do these equations. So that's the process of doing everything by hand. Usually I do that, but I working it by steps, so you don't have to draw the general outline like how I did it. Like you don't have to draw the Let me change the color to red. You don't have to draw this outline every single time. If like the general outline, you don't. It's not this all the time, but whatever the outline is for your equation, every single time you do the general outline, you don't have to. You just do everything by parts. So the first thing I'll do is that I'll do the derivative of f, and then I would multiply by this equation, and then I'm gonna add because that's gonna be a product rule, right? And then I have to have the regular of the f, and then you do the derivative of the second one. And then since I noticed that this second one, the derivative, I have to chain it, then I just chain it, basically. So I do the derivative of g, and then leave the a of x inside, basically, right here. And then I'm going to have to multiply by the derivative of a, right? So, and that's how I know. So just basically understand your rules, and you'll basically understand what to do. Products, just derivative of one equation times the regular equation of the other, plus the derivative plus by the regular equation by that equation, and then multiply the derivative of the other. Quotient rule, derivative of the numerator times the regular equation of the denominator, minus, because it's derivative of a quotient, plus it would be for the derivative of a product. So for a quotient, derivative of the numerator times the quotient of the denominator, minus the quotient by the regular equation of the numerator times the derivative of the denominator. All of that divided by the denominator squared. So the square of the denominator. And then the chain rule, whatever you do, you just work outside in. So you do the derivative of the first equation. So in this case, we have g of x and a of x. You do the derivative of g of x, and then you keep whatever's inside, which is a of x, inside. And then you multiply whatever that is left. So we did it right here. So this is our chain rule. So we had derivative of g of x, keep a of x inside. And then whatever's inside, you do the derivative of that. So you do the derivative of a of x and then x. So once you're done with all your equations, then you know your chain rule is done. So if there's like something else, like let's say there's a b of x inside, and inside that b of x is a c of x, right? So then you have to do then technically it'll be g of x, derivative of g times a of x, and then b of x inside that, and then c of x inside that, multiplied by the derivative of a, b of x inside that, and c of x inside that, because you still have those in. Now you're left with b of x and c of x inside. So you have to do a derivative of the b, because that's the one that's all the way outside. Other is the third one inside, the second one inside, because a is the first one inside. And then you have to do the derivative of b, and then do the derivative of c. It might seem like nonsense of what I'm saying, but if you follow the rule, it's basically it works all the time. So follow the chain rule, as I said like a few minutes ago, how it works, and then you'll get the general idea of how it works. And then you just do the general formula, and you'll get everything right. And that basically covers everything for the rules of limits and derivatives. Thanks for watching, and I'll see you at the next math record.